Hello, everyone. I was going to give some presentation on the current state of the zkFold symbolic DSL. And for this, I prepared a little showcase project. Let's check first that it works correctly. So it's just a simple Haskell project, which doesn't need any language plugins or something else. So it takes a while to compile because it involves some heavy type-level machinery, but yeah, it works just fine. Let's see if it works. So in main, I decided to just print out the circuit, one of circuits which we get during compilation. It's not very readable, but at least it works. And let's see what's inside. So what's the code? First of all, we need quite a lot of language extensions, but generally they are quite agreed that they are useful, needed. There are no questionable language extensions like implicit arguments or something like this. It's just extensions to the type system, and quite conservative at that. So because we write in Symbolic, we redefine some definitions from prelude. So we do not import it. We hide it and re-import some things we need from base libraries, from adjunctions. That's one of the dependencies we have. And so some of our symbolic base, it's called basic algebraic definitions. And so imports from zkFold symbolic itself. In the future, this whole, I'd say 90% of these imports would be re-exported by zkFold symbolic prelude once we have. So let's move to the code. So writing symbolic with predefined types is just too simple. So I decided to show some of the custom data types you can make with zkFold symbolic, and let's see how this would work. So first of all, let's see at the typical some kind of a domain business type called whole. It involves some sort of a count, which is encoded by 64-bit unsigned integer. So the first thing different, which is different in zkFold symbolic from usual Haskell, is the presence of this symbolic context parameter C, which is used in every field and well in the data type itself. It is used to encode the polymorphism. So this C variable can be either used to turn the code into circuits, arithmetic circuits, or to just run it in pure context. It's called so it's called also interpreting the symbolic functions. So it has the context. It's a 64-bit unsigned integer, and the last argument is the register size. So you can leave it to automatic. We'll discuss it later, or you can fix it to be here. It's fixed 16-bit. So each element of a base field would contain 16 bits of 64-bit. So this would take 4 registers to stop. And then 128-bit bytestring, which contains some kind of a data. So the first thing you want to do is to derive generic. After this, we can fill in some instances for you, which will be really useful for you to use later. So first of them is the SymbolicData instance, which says that, well, this is the data type which is usable inside the zkFold symbolic to perform some kind of general operations, if then else matching, and so on. And the second class called SymbolicInput, which just says that this data type can be used as an input to the function which is being compiled to the circuit. So not all the functions used in the zkFold symbolic has to be compiled, but ones that have to have their inputs to be symbolic inputs. Then the second one, second example, which is a bit more complex, is the one where we have some custom logic for symbolic input. So the thing is that well, the data types are encoded by some prime fields. We need to constrain the input somehow in order to just to filter out some garbage which might get fed in. So for example, for unsigned integers, you might want to have the inputs to be like stored, for example, for this, that each register has to be in range from 0 to 2 to the power of 16 minus 1, or something else. And you want bits in the byte string to be bits, exactly zeros and ones. So for this, the symbolic input method is valid, is used. This is just a function which, given data type, should return a bool in that context. So for example, I have the diagonal data type, which should contain 2 equal field elements. I know this is not really useful or has any meaning, but at least it shows the example. So in this, we just compare it for equality, and that's it. So when this circuit gets compiled, this isValid function is called, and the constraint is set that this isValid should equal to 1. So for example, if the x and the dy components are not equal, then the circuit would be unsatisfiable given these inputs. So just to show off, here's a polymorphic variant, which uses not only the fixed data type of a field element, it's like a single field element, but a general A, which is a symbolic data. So the generic deriving still works. And also, we can write down the same logic as was defined for a previous data type for symbolic input, but a little bit more general. This would look like this. We have a separate data class or type class called EQ, same as in Prelude. But in addition, we have a second parameter which tells so what is the result of a quality comparison. Here it's like Boolean in our zkFold symbolic language. And also the second point why I had to make this is just to note that while you can for sure define some custom business logic inside isValid, you still have to check that the components of your data type are still valid by themselves. So for example, if I had unsigned integers substituted for A here, I had to check that they are two correct. Otherwise, this would be not great. So moving on, let's see how we can define some smart contracts and some symbolic functions on top of this. So let's, for example, say that also, in addition to whole, we have some kind of a footprint which would be computed from the whole. The difference is that it has only unsigned integer, and the register storing strategy is different, just to show that you can vary it. So for example, here, it uses the auto register size, which means that it would greedily allocate the biggest register size possible. So still symbolic data and symbolic input deriving works. And in addition, so we can also have EQ deriving. It works just as fine. But the catch is that for auto, we need to add these constraints to like defer the type level computation until the context becomes known. Otherwise, the Haskell compiler wouldn't know what is the size of the register. So given all this, we can now define the function footprint, which works in an arbitrary symbolic context C, and given a whole C, would compute the footprint C. So it takes the whole, and there's some kind of an algorithm. So here, for example, I truncate the datum argument of a whole to 64 bits, then convert it to unsigned integer, and do practically the same with the count. So the count was also 64-bit, but in a different register sizes. So I converted via byte strings between the register sizes, which is fine. Then sum it and get the footprint. The algorithm is not important. It was just made to show how things usually work, how functions are usually written. And well, for the contract itself, it's usually a function which takes the context, the arbitrary symbolic context C, takes some arguments. For example, here we have a whole in the footprint, and should return a Boolean. For example, here we check that the footprint of the whole is equal to the second argument which we gave here. And well, that's it. And that's the whole like smart contract. And what do we do with it? We compile it. We just call the function called compile, and in the result we get the arithmetic circuit. So what is this? It's like it is a bit contrived. It's a complex data type. It has 4 type level parameters. First of them is the base field in which we compute. For example, for Cardano, this would be the BLS, the base field of the BLS curves. And well, and there are 3 more arguments which we will talk about later. And well, the main here.
Actually, it will be the scalar field. Probably.
Oh, sorry. So it should be it should be the scalar field. That's correct. Let's fix it. Okay, this works just fine. Okay. The warning is about an unused importer. Let's remove it. Yeah. Okay. Thank you. So yeah, and well, that was the result of the main which we have seen. So that was the this one circuit which got compiled. So this was like the happy path, quite short and concise. So everything is derived and everything's okay. Let's look into deeper parts of Symbolic. So for example, what if I want to write down the symbolic data instance by hand? Don't know why, but sometimes it happens. So it's just let's see what's inside. What do we have to do? So here we have a dummy new type for which we will write the symbolic data instance, and it is a function. Inside it there is a function which, given a filled element, would produce 2 things. First of all, it would produce a vector of 5 filled elements, but somehow this is not a vector 5 of filled element C, but C of vector 5. So from this we got to know that C, this context variable, is actually a thing which, given a functor, should produce a type. So in the future I'll say that the functor is packed inside the context. And the second one is the witness field. So you can treat it like the base field of a context, but there is a catch that it is not. So it's used for generation of vertices inside circuits, but it's not encoded inside the circuit. So it's like external to the circuit, but we can turn it into a variable just fine. For now, if you don't understand what this means, you can treat it just like the base field, but with some extra catch. So moving on to the symbolic data instance. Here we have 4 associated types. First of them is the context in which we compute things. For now, it's C, obviously. The support argument is all the types, all the data we need to turn the data type, which might be a function, into like a thing which is directly encoded inside the circuit. So for this, for example, we need a single field element C, and then it will return something that is encoded inside the circuit. Then the third argument is the layout. The layout is the functor, which gets to be packed inside the circuit, inside the data type. And the payload, the last argument, is the functor for storing witness fields. Here we need only to store only one single witness field, so we use par1 from GHC generics here. And there are 3 functions in symbolic data, 3 methods. First of them is arithmetize. Given a data type and its support, it should return the functor, the layout, packed inside the context. Here is straightforward. So we are given a function inside the dummy and given a support, which is a field element. Well, we call the function with the support. We get the pair and return the first component where the packed functor lives. The second function is payload, which does the similar thing, but instead of the packed layout, returns just the payload with the witness fields inside. So here it's also straightforward. You just pack the witness field argument inside par1. And the third function, the third method is restore, which given away from it's the inverse to arithmetize and payload at the same time. So given a function which from the support returns the layout and payload, it should return the data type itself. So it's quite simple here, but for example, we could have some more contrived data type, more complex one, where this would work differently. But here is just packing and repacking the functors once again. So that's the the overview of what has to be done in order to write down the symbolic data instance by hand. As you could guess, the most of it is uniquely determined by the data type. So there's the only way to write correct instance, and well, we have done it for you with generic deriving. So please use it instead of writing down these explicit things by hand. It was just to show you what's inside symbolic data and how to use it. So there's the 3 functions that you can call, and there are some a bunch of type families which you can use. Moving on, I would like to show you what's inside the symbolic. So we have this constraint pretty much everywhere, but what's inside it, how to use it. For this example, I'm going to use another new type. It's called one-hot. So the purpose of it is to have some kind of custom layout, which we will also cover later, inside of which we have several field elements, and we want them to be the sum of them to be equal to 1 always. So we, for example, call the function is valid. So the function is valid should check that the sum of the elements should be equal to 1. So let's see what's inside. So we leave the symbolic data instance to the deriving mechanism, and then let's see what's inside symbolic input. We could write it down as just retrieve the field elements from the field one-hot and sum them and check that it's equal to 1. How can we do it inside this symbolic class? What's needed? Well, first of all, the sum of them would be a single field element, so we call the constructor, and inside of it, we should have the par1 packed inside the context. So to construct these packed functors, we can call the function called from circuit f. It has 2 arguments. First of all, it has a single input argument, which we're going to use inside the circuit. So here it's the one-hot, this layout, this packed layout, this packed layout. And then we need something called circuit fun, which, given this functor, should return another functor called j, and then it would return the j packed inside c. So what's the circuit function? It's the function which, given a layout of ice, should return the result also of ice. So here it's given a custom layout and returns a par1. It returns a par1 because it has to be a field element. Why is it monadic? Why does it use do notation? Because inside we can use operation from the MonadCircuit interface. So it should be a monadic function, which given in f ice should return m of j of ice, where m is arbitrary monad circuit. So what is MonadCircuit? It's like the low-level DSL for constructing arithmetic circuits. It has a few primitive constructs. So first of all, it has a function called unconstrained, which, given a witness, so this W is exactly the witness field we have seen before, returns a variable inside the circuit. And as you might have guessed from the name, it returns it unconstrained. So it just turns the witness into a variable, stores it inside the circuit, and returns the variable. Then we can manipulate these variables to return them, just if they're ready, and maybe introduce some more witnesses. Also, well, finally, you also have to constrain the variables. There is a function called constraint, which adds the new constraint to the system. So this function expects the polynomial constraint. So you provided some polynomial p of x, and then it is expected that the p of x always returns 0, always evaluates to 0 on each and every correct inputs. And also a function called range constraint, which, given a variable and an upper bound, asserts that for this circuit to be satisfied, you have to have a variable to be in range from 0 to upper bound, all inclusive. So upper bound is okay, 0 is okay, upper bound plus 1 is not okay. And there are some also helper functions atop of it. So new constraint, you guessed, combines together unconstrained and constraint. So given a new constraint and new variable and the witness, it returns the new variable. And also new ranged, which given a range and the witness returns a variable which has to be inside the range. And finally, what is used here is called new assigned. So given a polynomial witness, it both creates a new unconstrained variable and adds a constraint that the new variable minus the polynomial provided here should equal 0. It's quite convenient because most of the operations we're going to use are anyway addition, negation, multiplication, some constants, so they fit inside polynomials. So let's call this new assigned to some variables inside the vector. No, it might be vector, it might be something else. So what we do here to compute the sum, actually, we finally arrived at it, we fold it inside the monad. So we need to provide two things. We need to provide the iteration, which, given that we compute the sum, should produce the new variable, which is the sum of the first two. And we should provide some seed, which in this case should be 0. And then, well, we feed it our custom layout and we get the sum. So to sum, we call new assigned. Here we just a shorthand for this thing. So given some x, we say that the ith witness plus jth witness is the result for the new variable, is the value of the new variable. And so that would be the partial sum of the container. And for 0, we could create it via new assigned const 0, but actually we can turn arbitrary base field into its corresponding variable by just calling from constant. So from our algebraic definitions, but you can use it here to turn any base field element into a variable. So that's the sum, we return it. We get the field element, which is called LSum, and we compare it to 1, to equal 1, and that's the function, the whole function. So that was pretty much it about MonadCircuit. One more thing is so how to use these witness fields. Back to dummy f, we have a second part of a tuple inside dummy to be witness field. How do we use it inside MonadCircuit? So we call once again from circuit f. We need some kind of a circuit inside it to build new constraints on top of it. So for this, we can pass the thing called HUnit. HUnit is like a trivial circuit which has zero outputs, and is just like empty circuit, and that's it. So we don't need its input. Then we create new unconstrained variable for the witness we stored inside dummy, and we return it. And then that's how the witness fields get encoded inside Symbolic. So they get their own variables. But the catch here, so why is this function called unsafe retrieve? Because, so as you can guess from the name, the variable is unconstrained. So there's no way to actually check if this is some meaningful field element or just some arbitrary thing. You usually have to constrain it somehow. So we have two examples in our base library for now. The first of them is the symbolic list, which cannot store all their elements inside the circuit. So it has to store their elements outside the circuit as these witness fields. And then how do we retrieve for example, the head of the list? We get the head, we turn it by unconstrained inside the circuit, and then additionally constrain it so that the hash of the whole list should equal hash of the tail together with this new head should equal the hash of the list itself. So that's the first application we have, and the second is like the general hashed data type, which stores the actual contents in the witnesses, in the payload, and inside the circuit, only hash is stored. And then to retrieve it's called pre-image of the hash, we get it from the payload and constrain it so that its hash should equal to the layout we have for it. So here's the thing, why even payload is used at all. So moving on, I promised that the one hot should have some custom layout inside. Let's see what's needed to have a custom layout inside zkFold Symbolic. So first of all, it has to be a functor, of course, and also it has to be traversable. It has to be traversable because we use it inside monadic interfaces a lot, and so we have to traverse over it. That's expected. And the last, actually, it has to be representable. So that's why we use the library called the junctions. It defines the representable type class inside. So what's the meaning of it? To be representable, a functor should be isomorphic to some kind of a function. So the rep associated type is the argument type of a function, and so the result type of a function is the functor argument. So for this custom layout A, for example. And so the two functions, tabulate and index, are witnesses to this isomorphism. So tabulate has to turn the function into this functor which is representable, and vice versa, index, given a functor and given a rep, so given argument, it should return the result. So for the vector, the isomorphism is obvious. So the rep should be something which has exactly 19 elements. If vector here is of the size 19, and well, we just index the vector, or vice versa, create the vector from a function by calling consecutively 0th element, 1st element, and so on. So that's it. And what's expected from the rep? There are also constraints on rep. Because, well, why do we have reps at all? Why do we have to use them? Because inside the circuit, they represent like the input vertices. So input vertex has to be ordered, has to be checkable for equality, should have a normal form. For this, we use n of data class from strict data, if I'm not mistaken, the name of the package is, and the binary class will like turn it to some binary representation. It's used internally for generating the variable indices, for generating vertices inside the circuit. Maybe I will go in depth sometime about how it is used and how does the algorithm work. And well, the superclass of the representable is the distributive class, which is converse to the traversable class. And for this, the generic definition distribute rep is ready, which if something is representable, something is also distributive, and the distribute rep is a witness to it. So you can plug it in just like this. So here's to the custom layouts. And moving on, I want to show you some other things in Symbolic class, which are also useful. So we have seen the main function, which is called from circuit F, which is like most useful of them all because it allows to introduce new constraints inside the circuit. But there are also cases where you just have to transform the outputs of a circuit somehow, and you don't have to introduce new constraints. So it's like some natural transformation on functors, if you know what I mean. For this, we also have some functions which are actually defined in the superclasses of Symbolic. First of them is an H-map, which you can guess from the name is the higher order equivalent of the F-map from the functor. So given a natural transformation between factors, it should be able to transform contexts. So from the one where the input of a natural transformation is packed to the one where the output transformation is packed. So for example, here from one hot, we retrieve one of the elements, fifth to be exact, first using H-map. So how do we do it? First, we get the one hot, which to remind you is the custom layout packed inside the context. And then we call an H-map, which should turn the custom layout into a par1. So first we unwrap the new type by calling the getter. Then we get the fifth element of the vector. Then we pack it back into par1. And then the hmap would return the par1 packed inside. And then we call the field element constructor to wrap this and to be able to use it as the symbolic data type. Moving on, we have also another function, which is an analog of applicative function lift@1. It's called hLift@a2. So once again, it expects the binary natural transformation. It expects two packed functors and returns the new packed functor. So it's just for demonstration purposes. So we need to have some dummy argument. Once again, it's hunit, so it's analog to the calling pure with to calling the pure from applicative with the unit type. So here, as the unit type, we have the U1 from GHC generics. And that's it. Well, it's never used, and then we do the same as before. So we get the same, exactly the same element, just in another way. So what can we do? Once again, in addition, what can we do additionally? Additionally, we have the class called package. So it's something new in comparison to previous analogies with the functors and applicatives. So moving on to package, what does it do? Its purpose is to unwrap, to unpackage the functor stored inside the circuit, stored inside the context. Sorry. So, for example, this unpacked, defined on top of package class, does this. So, taking a functor packed inside the context, it completely unwraps it. So, it returns the functor where inside of it are stored the context, which all pack only one output. So it's encoded by having the par1 as the packed functor here. So here we can unpack one hot. We get the custom layout. We call vector. We get the here we get the vector of size 19 with the C par1 inside. So we get the fifth of them. We get the C par1, and then we call it. We wrap it with field element, and that's it. And finally, what's actually defined inside the package. So here's the function called unpackWith. So the reason why we don't have unpacked defined completely inside package is because it does things too slowly and too definitively, I'd say. So it unwraps completely, unpacks completely the functor inside. This can be suboptimal because, well, if we combine circuits back together, we have to merge all the constraints we have inside. So if we, for example, completely unpack the vector, then completely pack it back inside, this would merge a lot of duplicate circuits. This is unfortunate. So we need something more granular. So the function defined actually inside package is called unpackWith. So given a way to peel back one layer of a functor inside the circuit, inside the context, it just peels it back by one layer. So if we by H get the composition of functors f and j, then we return the f as the outer part, which contains the circuits inside, and then the circuits only pack the j on the inner functor. So this is more granular and might help with writing some more efficient code. For example, the application we have, which I have in the back of my mind, is the function called chunks in bytestring. So how to chunkify the bytestring. Bytestring is stored as the vector packed inside the circuit, and so we call unpackWith to peel back a layer to just where inside we chunkify the vector stored inside, and then we get the chunks properly, effectively. So how is it used here? We call vector, and then fmap it by par1s. So the outer part becomes the vector, and the inner part is par1s. And then we get the fifth of them, and then we return it in the field element. So basically, actually, this is the definition of unpacked here. It's unpackWith, which fmaps inside. And well, as you can guess, the result of the lottery here would be always true, because these are all four equal for same elements exactly, and so this result should be constant 1. But well, we're not going to check it. We're going just to see how we can use the contract in different ways. So first of all, the simplest of the contexts is the interpreter context. So what it does, it just robs the functor, swaps the argument. So it's the simplest way to have a symbolic context to just run functions purely. So we, for example, if we get the vector of 19 elements in the base field, we can directly evaluate the lottery with the interpreter context and not construct any circuits at all. We just run the pure functions, and that's it. So first we wrap it into the custom layout, then we call the interpreter, and then we wrap it into one hot, because one hot had the context inside. So here it has interpreter context inside. Then we feed it to the lottery function, and we should get the bool of interpreter. So we unpack it, and the result is actually the interpreter of par1. Then we get from the interpreter the value back. So here from run interpreter, it's we get the par1 of a's, and call unpar1 to get the a exactly, and that's the result of the interpreted version of the lottery. This can be useful for plenty of context, but of course, the main thing you want to do with the symbolic functions is to compile them. So here we can compile lottery, and what's the result actually? So this is the circuit, which has quite intricate and long types, which we'll go in depth about later. Well, the resulting circuit you can also evaluate. So here it expects some inputs, which look strange, but we'll discuss them. We'll talk about them later. And well, the result should be just the same. So evaluate it and interpret it. It doesn't matter. So moving on to the arguments, actually to the arguments of the arithmetic circuit. What are these? I'd like to remind that A is defined as the circuit with the base field fixed. So all that's left is these three parameters. What are these? What do they represent? So actually, the first of them is the payload, just the same payload as in SymbolicData class. It's the payload of the support. So here we have somehow we have two inputs. I'll also explain why do we have two inputs but we had one input in the lottery function. So one hot doesn't use payload, so it's not needed, and well, also some phantom last argument also doesn't use payloads. Then we have the layout argument, so it's like the inputs to the circuit, and of course the first input is the one hot, so it has custom layout inside. So that's it. And once again, some phantom argument, which does not use anything, also doesn't use an input. So it's U1 here. And then the last one is the output. Here the output is Boolean, so it has only one field element inside, and it's encoded by par1. So it's layout. And well, that's it. Just compile lottery returns this circuit. Exactly. Circuit 1. What can we do with it? For example, first of all, how do we get rid of these phantom U1 parameters? We can use a more advanced function, which is called compile with. So what does it do? Compile with takes two more arguments. First of them is what to do with the result of the compilation. So what to do with the circuit before we optimize it. So it's so it can be any kind of a function as long as it takes a circuit and also returns the circuit. You can see that the layout also can change just fine. And then what do we do? Well, the third argument, so the last argument is the function to compile. The first argument is what to do with the result of the compilation. And the second is how to map the inputs. So the magic here is that we can have arbitrary inputs we'd like. So here we set the payload to just U1 and the input to just custom layout without any U1s here. And what does the should the second argument do? It should show how to map the new inputs, which we would like to have, into the old inputs, the inputs to the symbolic function which we want to compile. So the payload is constant, and the inputs are the custom layout which we feed into from here, and some unused input U1. There's that, but we can do more. But just a second, I forgot to explain why are these U1s present. So that's the effect of the way we implemented symbolic data for functions. So symbolic data for functions collects the support, and the support for it are the input arguments of the function, and also the support argument of the output. The support argument of the output, as you can guess, it is non-existent. It doesn't use the support. So it's so the proxy C, the proxy is used as the support argument, and well, the layout for the proxy is U1. So here's where the U1 comes from. And well, we showed how to get rid of it here. And then we can also do some more fun things with compile with. For example, we can remap the inputs to payloads and backwards. So for example, sometimes in proving protocols, it's useful that the output of the circuit becomes its input, and its input becomes its payload. So how is it done? Why is it done? Because we want, for example, instead of computing circuit directly, we want to ask the user to guess the output, or guess the output of the old circuit and feed it as an input, and not represent the input inside the circuit at all. So it's moved into the payload. So that's the use case. And how do we do it with compile with? So first we have to change the output of the circuit. So we use the first argument of compile with. We replace ID with the function called guessOutput, which just moves the output of the circuit to the input. So here so we have an additional input which should be fed to be equal to the output of the old circuit inside. Otherwise, the circuit wouldn't have the system of constraints which would be satisfied. And we have to map the inputs. So the payload is still not used, and so the payload in the lottery function is not used, but we used it here, so we have the custom layout fed as an payload. And we have the input, which is unused here first, and then we have the par1 from the guess output. So here, actually, this one is unused, so we just show it like this, just U1. So the payload, the input, we've seen it before. What to do with this U1? It doesn't come from this argument. It comes from the guess output. So the guess output produces this extra multiplication of functors because it had the U1 as an input in the first place. This one had the input as U1 in the first place. So we have to clean up to remove this U1 after we finish the compilation. There are also still some combinators to do this. So we had, for example, hmap to map the output, and we have hlmap to map the inputs, and hpmap to map the payload. And for the demonstration, here's the final example. Sorry. So for the final example, we're going to produce a circuit which doesn't have a payload, and whose inputs are exactly custom layout and par1. So this should be just the result of the guess output, which doesn't map the inputs in any way. So we call the compile with the guess output, and the comma to just group the payload and input back into the payload and input. So we don't do any transformation on the input here. And the result would be like this. So because we have like two inputs, one real and one phantom, which both don't use payload. We get u1 multiplied by u1 as a payload. Then after guess output, we get the input, which contains of the real custom layout and the phantom u1 as the first part of the multiplication. And as the second part of the multiplication, we get the output, the par1. And the output becomes unused, u1. So here we need to map both the payload and the input. We can do this with the functions, as I said, the hlmap and hpmap. So hlmap should map the new input to the old input, because because it's in the input position, so it's contravariant. So the new inputs are the custom layout and par1 from here. And then we just shuffle it around to fit the input of the circuit we got after compilation. And then hpmap should get the u1 from the payload here and construct some u1s for the payload in the circuit. Note that I pattern matched on u1 here, so actually I can remove the annotation here, and this would infer the types just fine. Would just warn me that it's a top-level binding with no signature, but otherwise it infers the types just fine. So that's it. Thank you for coming. If there are any questions, I'd be happy to answer them.